Hi everybody, so today we'll be taking a look at the Phlogopite Mica sheet from Snellius Minerals. The Phlogopite Mica sheet is an excellent contrast to the oriented muscovite mica sheet that we've looked at in previous videos. And I'd suggest before watching this video, watch the video on the oriented muscovite mica sheet. We're going to cover a bunch of similar concepts and we're going to go a bit faster with our Phlogopite sheet to keep this video shorter. Here is an example of one of the Phlogopite mica sheets from Snellius Minerals. These Phlogopite mica sheets are all cut and cleaved from natural crystals, and so there's some variability in sort of color and thickness in various things. Here's an example of one of the larger crystals that this is cut and cleaved from. Similar to our muscovite mica, our Phlogopite mica crystals can get rather large. If you'd like to follow along with the experiments that we're going to do today, you can pick up a Phlogopite sheet from the eBay store Snellius Minerals, and there's a wide variety of other very nerdy minerals there for sale as well. Let's start off our video today by taking a look at the big picture concepts that we want to think about when we're examining a mineral. Our minerals are defined by their chemistry and structure. This in turn determines the crystallography we'll see in our macroscopic crystals of that mineral, along with the optical properties that our mineral will also display. All of these concepts are linked together. Now, our Phlogopite has one of the most complicated chemistries and structures of any of the minerals we've looked at. However, it's very similar to our muscovite, so we're just gonna steal a whole bunch of stuff from our muscovite video. The chemistry of our Phlogopite consists of potassium, magnesium, aluminum, silicon, oxygen, and hydroxide. And the structure of our Phlogopite is of a TOT trioctahedral sheet silicate with interlayer potassium. The main difference between our Phlogopite and muscovite is that our Phlogopite has magnesium in its octahedral layer in its structure rather than aluminum. The aluminum in our muscovite structure is a +3 cation, and so what this means is our muscovite actually is a dioctahedral sheet silicate, and the dioctahedral term is referring to the two aluminum cations that are there to provide the +6 positive charge in the octahedral layer of our muscovite. Our Phlogopite has magnesium in its octahedral layer, and our magnesium has a +2 positive charge. This means we're going to need 3 magnesium cations in order to make a +6 positive charge in our octahedral layer, and our 3 magnesium atoms in our octahedral layer give rise to the terminology of trioctahedral. Now let's take a look at a simplified structure model for our Phlogopite, and this will be very similar to what we did in our muscovite video as well. For a more in-depth explanation of what's going on here, you can check out the Klein and Dutro reference I'll have at the end of this video, or also Mindat has some nice structure models as well. Our Phlogopite is a TOT trioctahedral sheet silicate. The TOT portion of that definition is referencing a tetrahedral layer, octahedral layer, and tetrahedral layer that are all bound together into a larger layer in the Phlogopite structure. Here, these larger structural units are represented by a blue rectangle. These TOT sheets overall are composed of magnesium, aluminum, silicon, oxygen, and hydroxide. The important thing for us to recognize today is that these structural units are bound together more strongly than the bonding that occurs between our TOT structural units. The bonding between our TOT structural units is from potassium ions. Our TOT sheets overall have a negative charge remaining on them, and in order to maintain charge balance in our Phlogopite, some additional positive charges are needed. These are provided by our potassium ions. The important thing to remember for us today is that the bonding within our TOT structural layers is much stronger than the potassium bonding holding those layers together. And this difference in bonding ultimately gives rise to the perfect cleavage that we end up seeing in our Phlogopite. Let's add on some crystallographic axes to our schematic view of our Phlogopite structure. And now we get to add on a bonus complication that has to do with the TOT layers in our Phlogopite structure. Our TOT layers are actually not well represented by a rectangle. A better representation would be a parallelogram, because there's actually a misfit in between the spacing of our tetrahedral, octahedral, and tetrahedral layers, and this misfit can be accommodated in a variety of ways. Adding on additional layers to our simplified structure model would allow us to explore polytypes for Phlogopite. However, that's worth its own nerdy video some other day. And the most common polytype shown by Phlogopite is 1M, which should work with this schematic that we have here. Thinking of the TOT layers in our Phlogopite as a parallelogram is actually quite a significant change from thinking of them as rectangles. This means the angle between our A and C crystallographic axes will no longer be 90 degrees, and the symmetry of our crystal structure will decrease from something that could have been trigonal to monoclinic instead. For the 1M polytype of Phlogopite, the angle between the A and C crystallographic axis will be right around 100 degrees. And at the scale of our simplified structure model, the symmetry that we're thinking about is our space group symmetry. For Phlogopite of polytype 1M, the space group symmetry will be C2/M. This is just a bit different from the space group symmetry of our most common muscovite polytype, which is C2/C. However, both of these end up with the same point group symmetry of 2/M. There isn't really a way to determine the difference between the glide plane in our muscovite compared to the mirror plane in our Phlogopite when you're looking at a hand sample. Let's go back out to the big picture overview of our Phlogopite. We've talked a bit about the chemistry and structure of our Phlogopite and also did a bit of comparison with muscovite that we looked at earlier. Additional important properties of Phlogopite that we should review include its hardness, which varies between 2 and 3 on the Mohs scale. Phlogopite also displays perfect cleavage along planes that cut only the C crystallographic axis of the Phlogopite. And this perfect cleavage is a result of the sheet silicate structure of our Phlogopite. The bonding between our TOT layers and our potassium ions is much weaker than the bonding within each TOT layer. When we pull apart Phlogopite sheets along this cleavage plane, what we're doing is breaking those potassium to TOT bonds. Back to our Phlogopite properties, the density of our Phlogopite is fairly low at 2.78 to 2.86 grams per cubic centimeter. And much like muscovite, our Phlogopite has some limited variability due to solid solution series that occur within its structure. You can have a bit of sodium substitute in for potassium, fluorine for hydroxide, iron for magnesium. These substitutions will affect the physical properties of our Phlogopite to some extent, so you can have variability in the density and variability in the refractive indices of our Phlogopite. Let's take a look at one of our Phlogopite mica sheets now and see if we can learn anything about its crystallography. One of the main things to note about our Phlogopite is that it is indeed a flat sheet, and this flat sheet generated by the cleavage of our Phlogopite is giving us crystallographic information. Our point group symbol for our Phlogopite is 2/M. This means that our B crystallographic axis is going to be a twofold rotational axis with a perpendicular mirror plane. Now, unfortunately, the edges of our Phlogopite sheet have no crystallographic information to give us. These edges have all been cut by me and are not crystallographically oriented. This differs a bit from our oriented muscovite mica sheet, and you'll see why later. So the crystallographic information we do have about our Phlogopite mica sheet is that we have these flat sheets that are generated by the cleavage of our Phlogopite mica, and the cleavage only cuts the C crystallographic axis of our Phlogopite. Let's bring back our simplified Phlogopite structure model, and as you can see here, the cleavages are going to occur where we can break the bonds between potassium and those TOT layers of our Phlogopite. The way this all works out is that when we're looking down onto one of these cleavage surfaces, what we're looking at is actually the plane of the A and B axes of our Phlogopite. Here's just a quick refresher on the crystallographic axes in the monoclinic crystal system. The A and C crystallographic axes of our mineral are going to lie in a plane that is perpendicular to the B crystallographic axis in our mineral. However, the angle between our A and C crystallographic axes will not be 90 degrees. Now, specifically for the crystal class 2/m, our B crystallographic axis is going to be a twofold rotational symmetry element, and the B axis will be perpendicular to a mirror plane which contains the A and C crystallographic axes. Usually when thinking about the orientation of minerals in the monoclinic crystal system, we have the C axis be vertical and the A axis dip down into the front. But for our phlogopite today, it makes more sense to think about what's going on when our A axis is actually horizontal. This means that our C crystallographic axis will be at an angle to vertical. Specifically for phlogopite, 10 degrees and 12 minutes, as the angle between the A and C crystallographic axes for our phlogopite is 100 degrees and 12 minutes. We'll go back out to our simplified phlogopite structure model. Hopefully the relationships between the A, B, and C crystallographic axis in this diagram make sense. We'll bring everything together now in thinking about the crystallography and the cleavage of our phlogopite. When we're looking down onto one of the cleavage planes of our phlogopite, we're actually looking down on the plane of the A and B crystallographic axes. Once we establish the location of the A and B crystallographic axes within this plane, then we'll also know the location of the C crystallographic axis as well. However, without additional crystallographic information, all we know right now is that we're looking onto that plane that contains the A and B crystallographic axes. The axes themselves could be rotated from the positions we're currently showing them at. They could be here, for example. And so we'll need additional crystallographic information before we can figure out fully what's going on. We'll now take a look at the optical properties of our Phlogopite mica sheet in order to gain additional information that will allow us to understand the crystallography of our Phlogopite. Back out to the big picture, we talked about the chemistry and structure of our Phlogopite, along with how our cleavage in our Phlogopite structure gives us some idea of crystallographic orientation. Now we'll take a look at the optical indicatrix for our Phlogopite. The optical indicatrix of our Phlogopite is a three-dimensional representation of the refractive indices of our Phlogopite. The refractive indices of our Phlogopite also do vary with things like solid solution substitutions. For simplicity, I picked single values for taking a look at our example optical indicatrix, but our natural Phlogopite will have some variation here. Here we have three different important views of the optical indicatrix for our Phlogopite. This shape is exaggerated for demonstration purposes, but our Phlogopite optical indicatrix is going to be a triaxial ellipsoid. The axes of this ellipsoid are going to consist of our refractive indices, alpha, beta, and gamma. The axial directions through this ellipsoid are referred to as x, y, and z, and these in turn are associated with refractive index alpha, beta, and gamma. If you'd like to learn more about biaxial materials and their optical indicatrices, you should check out the video Optical Mineralogy Biaxial Materials. Our Phlogopite is going to be biaxial negative. This means that refractive index beta is closer to refractive index gamma than it is to refractive index alpha. Our biaxial Phlogopite is going to have two optic axes perpendicular to circular sections through the optical indicatrix. And these circular sections have a radius of refractive index beta. The angle between our two optic axes of our Phlogopite is going to vary between 0 and 5 degrees. This is in part due to the variability of the refractive indices of our Phlogopite. Let's also mark where our optic axes emerge in our view to the upper left. We'll do this with two stars representing our optic axes. This will become important later. We can also label these different views of our optical indicatrix for the interference figure that they'll generate when looking down each view. This is pretty much all the information we'll need when thinking about the optical indicatrix for our Phlogopite. However, we should now add in an additional layer of complication thinking about how our optical indicatrix lines up with our crystallographic axes. For our monoclinic crystal system, this isn't as straightforward as one would hope. We'll first remove a bit of information to tidy everything up here, and now let's add in the relationships between our crystallographic axes and the directions of our optical indicatrix. Our Phlogopite is monoclinic, and this means that only one of our crystallographic axes and the axes of our optical indicatrix are going to coincide. In this case, the y direction through our optical indicatrix will be the same as our B crystallographic axis. Our C crystallographic axis will vary between 0 and 5 degrees from our x direction of our optical indicatrix, and our A crystallographic axis varies between 5 and 10 degrees from the Z direction through our optical indicatrix. Remember, the angle between our A and C crystallographic axes is 110 degrees and 12 minutes. Let's add on a representation of how our crystallographic axes and our optical indicatrix line up. As you can see here, these relationships are fairly complicated, but there's an important point to be made because of this. The optics of our mineral are related to the symmetry of the structure that we're looking at. This is why only the B crystallographic axis aligns with one of the axes of our optical indicatrix. It's because the B axis is our twofold rotational symmetry element with perpendicular mirror plane. Remember, the chemistry and structure of our mineral control the crystallography and optical properties of our mineral. All these concepts are linked together. Now that we've taken a look at the optical indicatrix for our Phlogopite and have tied together our optical indicatrix and our crystallographic axes, we can figure out what view through our optical indicatrix we'll see when we're looking onto one of the cleavage surfaces of our Phlogopite. The cleavage plane in our Phlogopite is the same plane that contains the A and B crystallographic axes. And although we don't currently have a view through our optical indicatrix that exactly coincides with this plane, the view of our optical indicatrix in the upper left is within 5 to 10 degrees of the view we're looking for. Let's focus a bit more on this view for a moment. When we're looking down the x direction of our optical indicatrix, what we'll see is the gamma-beta plane of our mineral. And because our Phlogopite is biaxial negative in this plane, we would generate a BXA interference figure. That's an acute bisectrix interference figure. And the optic axes of our Phlogopite are going to be located approximately where the stars are in this figure. Once again, the 2V angle in our Phlogopite has some variability based on the variability in the refractive indices of our Phlogopite. So if we're viewing our Phlogopite while it lies on a cleavage surface, this is the view of our optical indicatrix we're almost looking at. As there is some variability between the x direction of our optical indicatrix and the C crystallographic axis, as well as the Z direction of our optical indicatrix and the A crystallographic axis, the actual view of our optical indicatrix when looking at our Phlogopite lying on a cleavage surface will be slightly different. And here's a possible representation of that view depending upon those angles between our crystallographic axes and the directions of our optical indicatrix. So you can imagine we've rotated our 3D optical indicatrix just slightly. We can still see refractive index beta in this view, however refractive index gamma has been replaced with gamma prime, a value between beta and gamma. However, gamma prime is going to be very close to gamma as we've only rotated 5 to 10 degrees from our original view of our optical indicatrix. We should still be able to generate a pretty good almost BXA interference figure with just that slight rotation. Now let's take a look at our Phlogopite mica sheet and translate all our theoretical understanding of our optical indicatrix into practice. Here we have our Phlogopite mica sheet, and we're currently viewing our specimen with transmitted plane polarized light. We'll first rotate our sample in plane polarized light to see if we can see any pleochroism. This particular specimen is rather boring. These are all natural crystals, and so there is some variability here. However, you'll see in a moment why this particular specimen is not displaying pleochroism. Let's bring in our upper polarizer now so we can view our specimen with crossed polarizers. Now we'll begin to rotate our specimen with crossed polarizers, and I want you to notice that, well, it mostly is just staying extinct. What this means is that we must be looking down one of the optic axes of our Phlogopite in order for it to display this behavior. And this is well within the realm of possibility given the small 2V angle of our Phlogopite and the axial relations between our crystallographic axes and the directions of our optical indicatrix. In order to figure out what's going on here, we should bring in a converging lens and generate an interference figure. What we should see is a biaxial optic axis interference figure. When we bring in our converging lens, however, we see a uniaxial optic axis interference figure. We have a couple options to explain what's going on here, and this will help us to better understand the differences between our biaxial and uniaxial minerals. If we take a look back at our refractive indices for our Phlogopite, I want you to notice that beta and gamma have the exact same value ranges. For our example biaxial optical indicatrix for Phlogopite, I picked two different values for beta and gamma. But it's worth thinking about what occurs if beta and gamma are actually the same value. If beta and gamma are the same value, our optical indicatrix is actually no longer a triaxial ellipsoid, and we end up with a uniaxial optical indicatrix. You can sort of think about uniaxial materials just being a special case of biaxial materials where the 2V angle is equal to 0. Why are we seeing an apparent uniaxial optic axis interference figure for our Phlogopite? Well, it could either be that our Phlogopite is actually biaxial and just has such a small 2V angle that I can't really tell the difference between slightly biaxial and uniaxial. This would mean that refractive index beta and gamma are very, very close to one another. Or perhaps our Phlogopite is the trigonal polytype of Phlogopite. When we looked at all our Phlogopite properties earlier, we were actually looking at the most common polytype, which ends up being monoclinic. Other polytypes exist, however, with trigonal symmetry, and that could be what we're seeing here. I wouldn't definitively say that without lots of further tests. Even with this complication, our Phlogopite sheets are an excellent contrast to our oriented muscovite mica sheets. While our mica specimens might not look that different to the naked eye, with our optics we can easily tell our muscovite and Phlogopite apart. The BXA interference figure of our muscovite mica is in sharp contrast to the uniaxial optic axis interference figure of our Phlogopite. This also comes with a drawback for our Phlogopite, however. With the BXA figure for our muscovite, we were actually able to use the mellotopes of our muscovite to place the B crystallographic axis appropriately, thereby fully figuring out the crystallographic orientation of our muscovite. With our uniaxial optic axis interference figure for our Phlogopite, we don't have enough information from this to do something like that. And that's because if our Phlogopite is truly uniaxial, and we're truly looking at a trigonal crystal of Phlogopite in this moment, our A-axes are all the same, and so you are unable to differentiate them using optics. Once again, however, I'm not sure in this instance if our Phlogopite is truly uniaxial or biaxial with a very small 2V angle. We'd need further testing. Let's review what we talked about today. We looked at experiments that you can do with the Phlogopite mica sheet from Snellius Minerals. We first looked into background information about the most common polytype of our mineral phlogopite. But maybe we really should have been looking into background information on the less common trigonal polytype of our phlogopite. Then we talked about a simplified structure model of our phlogopite. There's a more complicated trigonal version for this too. It involves a screw axis, so I'm not gonna try and make that. Then we talked about the crystallography of our phlogopite. But once again, maybe we should have been looking at the trigonal version, more like this. And of course, we investigated the optical indicatrix for our phlogopite. But if our phlogopite is indeed trigonal, we should have probably been checking out this optical indicatrix instead. All of this comes back to when we looked at the optical properties of our phlogopite, and when we generated our interference figure for our phlogopite, it looked pretty uniaxial. So, is this actually a uniaxial optic axis interference figure, or is this just a biaxial interference figure with such a small 2V I can't tell the difference? I genuinely don't know, and we need additional tests in order to figure this out. It's always a good idea to understand the limitations of the techniques you're applying. Even though we're not sure if our phlogopite is truly biaxial with a very small 2V angle, or uniaxial and the trigonal polytype of phlogopite, we can still use our optical properties to differentiate our phlogopite and muscovite fairly easily. Unless we end up with muscovite that is also the trigonal polytype. The phyllosilicates are pretty complicated. But if you buy your oriented muscovite mica sheet from Snellius Minerals along with your phlogopite mica sheet from Snellius Minerals, I'll make sure they're different. And note the question marks in my labeling of our phlogopite mica sheet to denote the uncertainty about whether it's truly uniaxial or not. If you're interested in trying these experiments out on your own, you can pick up one of the Phlogopite Mica sheets from the eBay store Snellius Minerals. And if you have any questions, comments, or concerns, feel free to reach out to me at snelliusminerals@gmail.com. Here are the references I consulted in the construction of today's video. In particular, check out Klein and Dutro if you want to learn more about polytypes. Thank you for watching, and have a great day.